very happy with Luca to tell us about flatspace holography for supersymmetric images.
Great. That's loud. Thank you very much for the invitation. Yeah, so today I'll be talking about flatspace holography for a special observable, a supersymmetric index. And this is based on a number of projects, some of which have appeared, some of which have appeared, some of which are in progress, with Joaquin Riachi, Samir Murthy, Roberta Paran, and Jan Borl, who's in the audience and has been doing the heavy lifting. So I'll start with something a little bit corny. What is the dream of holography? So, in my opinion, the dream of holography is that for every object that we have in gravity, we have an associated dual quantum system. So, for example, that we can replace a black hole with a dual quantum system, and this should be applicable regardless of the asymptotics of the space-time. So, even in a space-time that is asymptotically flat, we would like this to be true. And to rephrase this in Euclidean signature, we could say that the partition function of the gravitational object is captured by the Gibbons-Hawking prescription, where we choose the time to be periodic, and we turn on some boundary sources g of x, and there's some dictionary that computes the partition function of the dual quantum system with those quantum sources. And again, I emphasize that we would like this to be true regardless of the asymptotics of the space-time. And we realized this dream in the context of ADS-CFT. We realized this dream in the context of ADS-CFT. Namely, there we consider a stack of d-branes typically in asymptotically 10-dimensional or 11-dimensional flat space. We put that stack somewhere. We take the temperature at infinity to 0. And that stack backreacts on the space-time, and the space-time takes the form ADS-D times some internal manifold. That adds up, such that the number of dimensions adds up to 10 or 11. So in this language, computations in ADS-CFT can be viewed as capturing properties of extremal black strings or extremal black branes in flat space. And I'm sure you all know about this. And the other thing we all learn about is that to make ADS-CFT work, we usually actually get rid of the flat space region. So we put our holographic screen at the boundary of ADS. And we say that the physics within ADS is captured by the CFT that lives on the boundary. So we don't really care about what happens in flat space. We can neglect that. But today, I don't want to neglect that. And I want to ask if we can go away from the decoupling limit in a controlled fashion. And the answer will turn out to be yes, for at least some of the observables in gravity, namely for observables protected by supersymmetry, for instance, for supersymmetric indices. So why would indices be helpful to achieve this goal? Well, let's imagine that we have a gravitational system that is dual to some putative quantum system. And we try to compute an index, which is the same as a partition function, but weighed by -1 to the fermion number. Oh, there should be a minus in front of beta h. And we fix all of the charges of this gravitational object, and in the associated quantum system we go in a sector of fixed charge, and we compute this partition function weighing fermions and bosons oppositely. If the system that we're interested in preserves supersymmetry, all the states that are not protected by supersymmetry, that are not BPS, will turn out to have equal energy levels in flat space. So their contribution will cancel, and the only contribution will come from the BPS states whose energy is dependent on their charge. So it depends just on the charges Qi. And the non-trivial information that this index will capture is the difference between the bosonic and fermionic degeneracies. But this index has a trivial beta dependence. Yes?
So do I fix a particular representation of your supersymmetry algebra?
No, I just mean that you go into a sector with fixed charges for all bosonic symmetries in your theory. So you could choose to fix a set of charges that, you could choose a set of bosonic charges that commute with the supercharge and fix all of those. You won't be able to fix everything because this -1 to the f is still like a chemical potential for one of the bosonic charges, be it an angular momentum, or a symmetry charge, whatever you want. So if we can really view gravitational objects as dual to quantum systems, even in flat space, this formula should help us interpolate between the decoupling limit, namely the zero temperature limit, and the finite temperature limit to find gravitational solutions that capture the index of the same quantum system regardless of whether we have an ADS region or not. And today I'll discuss two examples of this, one for which we don't know the quantum system that fully captures the quantum mechanics of the gravitational object, namely the index of black holes. And one for which we do know what quantum systems captures the physics of the gravitational object, namely the index of black strings. Now, indices have long been associated with taking a decoupling limit to begin with. So, for instance, one of the hallmark results in string theory is that people have computed a string theory index at weak string coupling and matched that result, the logarithm of that result, to the area of an extremal black hole in the sector of fixed charge. And extremal black holes have an ADS frot, ADS2 frot, so it's essentially like taking the decoupling limit. However, I want to emphasize that this is a misconception. And there's three reasons why this equality has a misconception. Well, the reason number one is that the right-hand side, the area of an extremal black hole, is at most a degeneracy that's only defined in the zero temperature limit. The index on the left-hand side exists at arbitrary temperatures, right? So it should exist even away from the decoupling limit. The second misconception is that the left-hand side counts bosonic and fermionic states with opposite sign, but there's no reason why in the right-hand side the area of a black hole should weigh bosonic and fermionic states with an opposite sign. And finally, the index captures more contributions than that of the area of a single black hole. In fact, it captures contributions from other extremal solutions that could contribute to the left-hand side, for instance, multi-center black hole or black string solutions. So how do we account for those if on the right-hand side we only have an area? And just to emphasize this even more, in fact, even from the beginning of ADS-CFT, there was a long-held belief that indices on the boundary side receive no contribution from black hole solutions. And this kind of followed from, this is somewhat, paradoxical belief given that Strominger and Valpa relied on an index to capture the area of a black hole. But this belief came from the fact that in the left-hand side, in an index, fermionic fields have to be periodic around the thermal circle. The thermal circle in a black hole background is typically contractible, and that's not allowed if you have periodic fermions. So that's where the belief came from. So today I also want to tell you why that belief is wrong. Okay, so I'll start with the simplest possible example in which we can go away from the decoupling limit. Namely, let's imagine that we have an extremal standard Reister-Nordstrom black hole. And instead of trying to compute the area of this black hole, let's instead try to go away from the decoupling limit to have a front that has finite size and compute an index instead. So first off, how do we compute an index in gravity? And why was this belief regarding the periodicity of the fermions wrong? So To compute an index in gravity, we have to reinterpret what this minus 1 to the f is. This minus 1 to the f indeed puts a boundary condition for fermionic fields to be periodic around the thermal circle. But there's another very useful way in which we can reinterpret it, which is that it's e to the 2 pi I times the angular momentum of states within the theory. This angular momentum is half integer quantized. This is the same as minus 1 to the f. So when we compute the partition function, if we input a chemical potential for an angular momentum, that's typically the same as saying that we have an angular velocity. So instead of looking at black holes that don't rotate, as you would in a standard partition function, this rewriting suggests that we should instead look at rotating black holes whose angular velocity is given by this equation. The Euclidean angular velocity times beta is a multiple, an odd integer multiple of 2 pi, right? This will introduce an e to the 2 pi ij chemical potential. Now, it turns out that most of these values of n will not be relevant. The only relevant value of n will correspond to 0 and minus 1. But I won't go into the details of why that's the case. Please ask me afterwards if you're interested. So let's analyze a little bit what happens to the topology of the space-time in the presence of this angular velocity. So when we go, since we're computing a partition function, we need to look at a Euclidean solution. So we need to do a left rotation. And that makes, puts an I in front of the angular velocity as well. And in a rotating black hole, it's actually a misconception that, well, it wasn't a misconception. People just didn't think about rotating black holes, but it's the fact that the thermal circle is in fact not a contractible circle. It's a combination between a thermal circle and a circle around the axis of rotation of the black hole that becomes contractible. Now, huh? No, they didn't think about it for the index. Yeah. What I meant was they didn't think about that implying this and this. Yeah, sorry about that. Yeah. That's why I hesitated at first, because people wrote this equality a long time ago. The misconception was about the index. Okay. So let's plug in the value that minus 1 to the s suggests us that we should take. Namely, that we should take beta omega is equal to 2 pi. So this is now our contractible circle. And this implies that since this is a contractible circle, fermions should be antiperiodic around this circle. On the other hand, the circle phi going to phi plus 2 pi is also a valid contractible circle, right? It contracts at the north and south poles of the sphere. So if I do another rotation by 2 pi for a fermion, if I just do a rotation by 2 pi without doing the rotation in phi, the fermion should gain another minus sign. So this implies that the fermion, with once I introduce this angular velocity, is precisely periodic around the thermal circle, which is precisely the boundary condition that is needed for an index. So this checks out. So given this, let's actually check just for the Kerr-Newman solution what the free energy of such solutions is. Because in principle, the free energy should also have the structure of an index. So here, because the free energy of a Kerr-Newman black hole is somewhat complicated to express in one slide, I just expanded the free energy at very low temperatures, so a very large beta, just to get you a sense of what's happening. So this is the first non-trivial term in beta that we find. So it depends on the angular velocity. However, notice that something very special happens when beta omega is plus or minus 2 pi. This term cancels, and in fact you could go to more and more subleading orders in beta, and you'll find that this cancellation is exact. So what you're left with is that the free energy of a Kerr-Newman black hole just takes this very simple form. And this is precisely the form that the logarithm of an index should take. This is the ADM mass, associated to a black hole. Sorry, the ADM mass that's BPS in the case of an index. And this is the entropy that captures the logarithm, the logarithm in the difference between bosonic and fermionic states, and it so happens to exactly agree with the extremal entropy of the black hole. So this explains why all these results that computed extremal entropies were in fact somewhat correct in computing the index. It's another way to say it is that the black hole in the limit when beta goes to infinity has zero angular velocity. So in some sense, these solutions, if I think about them as a function of beta, these solutions, when I take beta to infinity, actually approach the extremal solution. But they have this special feature that their energy has their free energy has a trivial dependence on beta, just linear. And the special thing that one can notice about this geometry, literally this is just the Kerr-Newman geometry that you find in a GR textbook, is that if you plug in omega to take this value, you find that this geometry has a killing spinner. And there was a long-held belief that there were no geometries that were supersymmetric besides the extremal ones, but it turns out that that long-held belief is also wrong. This is an example of a finite temperature black hole that has a killing spinner. It's just a Euclidean solution. Okay, and instead of computing the action of this black hole, you could also use the thermodynamic relation to try to compute the free energy. So instead of computing the on-shell action explicitly, you could sum up the area of the black hole, beta omega j, and beta times the mass. And so not surprisingly, you get exactly the relation that I wrote on the previous slide, but what I want to emphasize is that the area of the black hole and the angular momentum terms themselves depend actually very non-trivially on the temperature of the black hole at infinity. So there's a non-trivial cancellation happening in the sum between these two terms that makes the index have an overall trivial beta dependence. And for the experts in the room, this cancellation is a baby version of what I think in the 90s was called the attractor mechanism. And I'll explain more in the slides to come. So the take-home message for these first 15 minutes is that there are flat space geometries at finite beta that still capture the same index as the one in the decoupling limit. So we took the geometry, turned on a rotation. The rotation is such that the circle, the sphere rotates by exactly 2 pi as you go around the thermal circle, and you magically find an index. Now, the second take-home message is that the free energy of such black hole has trivial beta dependence, even though individual characteristics of the black hole, like their area or angular momentum, do have very complicated beta dependence. And finally, there was actually no need to introduce this angular velocity. Well, this angular velocity gave the only type of geometry that fills in the space-time with these boundary conditions in which the fermion is actually periodic. And this is not a special case. There's in fact a much vaster set of allowed contributions to the index. And the way to find them is you look in 4D, let's say if you're interested in 4D indices, and you just impose that there should be a killing spinner and that your space-time should be asymptotically R3 process 1. And you get a whole family of solutions called multi-center black hole solutions that people knew about at 0 temperature. So these solutions can be described in terms of 2 harmonic functions, u and u tilde, and an angular velocity, omega, that depends on the position where you are. And this xi gives is what's called a base space. It's a space that has a non-trivial emblakening factor as we move throughout the space that depends on u and u tilde. So the constraints of supersymmetry tell you that u and u tilde are harmonic functions, so they can be written as a sum over poles. And to get that the space-time is asymptotically R3 process 1, or it's asymptotically Minkowski space, it turns out that the number of poles in U and the number of poles in U tilde have to be the same. Otherwise, it will get what's typically called the Taub-Nut space. Good. And these type of solutions were actually studied in the past, starting with Cardinal and Hawking and Israel and Wilson. So we have to restrict to harmonic functions that have an equal number of poles on the left and to the right. But we haven't yet studied the smoothness of the space-time. And you might be naively worried that because U has poles, that this space-time actually contains singularities. And that's a very valid worry. In Lorentzian signature, if you want the space-time to have no naked singularities, it turns out that you have to make U and U tilde to have the same poles. This means that the blackening factor has double poles, and that's something that people typically encounter in extremal black holes. So when you put xi equal to xi tilde, you could solve the rest of the equations of motion. Omega becomes 0. There's no rotation in the space-time. And the type of solutions that you get are called Majumdar-Papa-Petru solutions. And they're the type of solutions that people discuss when they discuss ADS2 fragmentation. Each one of these points that corresponds to a pole corresponds to an infinitely long ADS2 throat. And there could be other ADS2 throats connecting them in a non-trivial way. Now, in Euclidean signature, imposing smoothness actually gives you a much more non-trivial constraint. So remember, we are just solving for the most general geometry that satisfies equations of motion and supergravity and has a flip spinner, and then we're imposing smoothness, and we're getting this non-trivial relation between the residues and values of the harmonic functions at different poles. Now, if you check what the thing that appears on the left-hand side, so this is a non-trivial relation as a function of the temperature. This is kind of analogous to the type of constraint that we impose when we try to find the periodicity of the time circle in Euclidean signature for a black hole and impose that there's no conical singularity at the Euclidean horizon. Now, if you actually compute what the left-hand side is, it turns out that the left-hand side is precisely 1 over the angular velocity for the horizon of each one of the black holes. You unfortunately have to trust me on this, the derivation is slightly complicated. But this implies that the most general solution that has killing spinners, that is smooth, actually automatically computes an index. It just comes out that beta omega is 2 pi. So this allows you to take the multi-center extremal solutions that are in equilibrium because their mass is equal to their charge, and now actually put them at arbitrary temperature to find their contribution to the index. And there's a whole moduli of solutions. So each one of these throats is it becomes finite. The horizon is a finite proper length. And each one of these black holes is rotating around its own axis. And there's an entire moduli space of solutions characterized by the relative angle between the different axes that the black holes are rotating around. So the only common property of these black holes is that as you go around the thermal circle, each one of these black holes does a 2 pi rotation. Okay, and you also have to impose the 2n-1 constraints that you get from smoothness. That also somewhat constrains the positions of the black holes. The poles in the harmonic functions x and u and u tilde this time actually become the north and south poles of the black holes, and the horizons actually correspond to a set of Dirac strings that go in between each pair of poles. Now, the simplest case is with when there are only 2 poles in the harmonic function, in which case we actually find that at finite temperature, this complicated solution just reduces to the Kerr-Newman solution that we discussed previously that has beta omega equal to pi, that also has killing spinners. And we can also compute the overall index of such solutions, and they just take the form of a sum of indices for each individual object in the space-time, which is kind of cool. So again, there is a trivial beta dependence, meaning that we can interpolate between the decoupling limit and the finite beta limit. Now, these black holes are black holes in pure supergravity. But if we want to study a bottom-up construction of flat space holography for supersymmetric indices, we should look at solutions that exist in string theory. So what about black holes and black string solutions in string theory? So these black holes, the only main difference is that the type of supergravity theories that we're interested in have vector multiplets. So this means that there is a set of scalar fields throughout the space-time, and I can set the value of the scalar fields all the way out at asymptotic infinity. And these solutions were extensively studied in the 90s, starting with Ferrara, Kalosh, and Strominger. The purpose of understanding these solutions was precisely to understand why, well, not only, but one purpose was to understand why indices don't change as a function of coupling. So the attractor solutions have had the feature that if I chose arbitrary boundary conditions for the scalar fields at asymptotic infinity, the properties on the horizon were independent of those boundary conditions. We'll see that that's no longer the case. So the solutions that we're looking for are solutions in R4 times the Calabi-Yau. And these were the extremal solutions that people studied in the past, and we're looking to put them at finite temperature, so have an additional thermal circle. And at infinity, we're still going to fix the boundary conditions. The new ingredient is that we'll fix the boundary condition for some scalar fields to some arbitrary value. Now, we can again start with the same strategy and find the most general solution that has a killing spinner. And it turns out that this is the most general form of the metric that has a killing spinner. Here, this factor is called an entropy function. Depends, again, on a harmonic function, but it has a more non-trivial form. It depends on the exact potential of the supergravity theory. But again, the physics is in these harmonic functions. So, again, we can look at what happens if we take these solutions and impose that they're smooth, that there's no naked singularities. Well, in Lorentzian signature, it turns out that the function sigma of h, the entropy function, has double poles. Again, so it's like the emblackening factor having double poles. And these double poles lead to an infinite front. And it's because of this infinite front that, in some sense, the boundary conditions that are all the way out at real asymptotic infinity get washed out by the time you get to the horizon of the black hole. By the time you get to the horizon of the black hole, the area of the black hole and the value of the scalars on the black hole are completely independent of the boundary conditions on the right. Now, if I instead impose smoothness in Euclidean signature, unsurprisingly, you'll find that the smoothness condition implies that beta omega is equal to 2 pi once again. So again, we're back to the case of computing an index. The special thing now is that the properties on the horizon, the values of the scalar on the horizon, and the value of the area of the horizon, are all actually dependent on the boundary conditions at asymptotic infinity. But again, magic happens. And if I look at the thermodynamic relation that combines the area with beta omega j to compute the free energy of the black hole, even though each individual term depends on all the moduli and temperature of the theory, the sum of the two terms is only dependent on the charges. So here, P and U are two of the charges associated with the harmonic functions. They're the D0 and D4 charge in this example. So, in some sense, this is the new form of the attractor mechanism. It's no longer that the property of the black hole, it's of the geometry itself, is independent of the boundary condition. It's that the observable itself, the index, is independent of the boundary conditions. And this is guaranteed by the smoothness of the space-time. And just as before, because at the limit when beta goes to infinity, omega becomes 0, the black hole asymptotes to the extremal solution, and that explains why we're recovering exactly the entropy at extremality. So more generally, we can compute, we can impose smoothness and compute the ionical action exactly, not relying on any thermodynamic relations, and we always find the same result. We find that the total action is the sum of two terms. One is the one that always reproduces the extremal entropy. This is why this function is called the entropy function, because when you evaluate it on the charges, it gives you the entropy of the extremal black hole, and the term that captures the ADM mass of the BBS state. So even though the index of some of these black holes has been computed in string theory, we don't actually have a boundary CFT description for the entire geometry, right? We don't have a CFT description for the ADS2 probe. So what we would like is to go away from the decoupling limit in a canonical example of ADS CFT, to really move a CFT that we know about into flat space and see that we can compute in a flat space solution properties in the CFT. And for this, we need to go to higher dimensions, right? Just using 4D flat space, we cannot obtain something that's higher dimension ADS, higher than 2 ADS, times an internal manifold. So the minimal number of dimensions in which you can do that is 5. And you can do that by doing a physical procedure called an uplift. So instead of trying to take the solutions that look like R4 times Calabi-Yau and putting it at a finite temperature, you could introduce an additional M-theory circle and uplift the solutions that we already know about that compute an index to ones that are now at finite temperature when measured with respect to asymptotic infinity. And on the left-hand side, these class of solutions included the ADS-free cross S2 times Calabi-Yau geometry that is dual to the two-dimensional MSW CFT. So as far as I know, this is the one with the minimal number of total dimensions that become flat. The idea is that one of the scalars in our four-dimensional theory, of supergravity, actually parametrizes the size of the M-theory circle. And we can just compute the new solution in which the size of the M-theory circle just varies. So we take our attractor saddles for 4D black holes that compute indices, and we can study what happens if I introduce different charges in the vector multiplet in which the scalar that parametrizes the M-theory circle lives. And if I set that the corresponding charge to be equal to 1, and I take the ratio between the M-theory circle and the Planck length to infinity, one finds, again, a black hole solution. So one finds black hole solutions not in R3 cross S1, but on R4 cross S1 that compute a 5-dimensional index. So the topology of the horizon is S3 in this case. If instead you take the solution that has 0 charge associated to that vector multiplet, you get attractor saddles for 5D black strings that compute an index in R3 cross S1 associated to the M-theory circle and S1 associated to the thermal circle. And the topology of the horizon that you find is S1 cross S2. Now, there are several, I will forget about the 5D black holes because they're similar to the 4D black holes, kind of boring. And I'll only focus on the black string solution. So what happens if I take the 0 temperature limit of the black string? Well, it just becomes the ADS-free cross S2 times Calabi-Yau solution that has no angular velocity in it. And this is the solution that was dual to the MSW CFT. Now, if I change the ratio between the size of the M-theory circle and the 5D temperature to be finite, and I zoom onto the near horizon region, I actually no longer find a near horizon region that has a finite temperature. I find that there's an effective temperature in ADS-free that becomes non-zero. So even though the temperature at asymptotic infinity is 0, the solution that I'm finding in ADS-free is corresponding to a BTZ black hole. And this is precisely the BTZ black hole that computes the index of the MSW CFT if you forgot about flat space to begin with. Okay? And finally, if you take beta 5D to be finite, so both these limits were in the limit of 0 5D temperature, if you take beta 5D to be finite, you just get a finite throat. The ADS-free gets eliminated entirely, and you get a black string whose horizon topology is, or ring, depending on terminology, whose horizon topology is S1 cross S2, that has computes an index because it's rotating in S2 at the same time that it is rotating on S1, and does exactly a 2 pi period around this sphere when moving around the thermal circle. So what do all these solutions have in common? Well, their Euclidean action actually is equal, and is equal to the following quantity, which is precisely the index of the MSW CFT. So here, gamma 0 is the D0 charge, and CR is a combination of the other charges that conventionally just reproduces the central charge of the CFT. So even though we're looking at solutions that don't have any ADS-free whatsoever, the index that's associated to these solutions is the same as that of the CFT. So we're just seeing the quantum system now at finite temperature with respect to 5-dimensional flat space. Okay, so the take-home message is that we found solutions that contribute to the index. They all have a finite throat. Their topology, they could either be black hole, black strings. We could, in principle, find black brains. Any solution that you're used to in ADS-CFT, we could probably move it away from the decoupling limit and compute that index. That would be my guess. So they take everything away from the decoupling limit, and for instance, in the case of ADS-free, they eliminate the ADS-free portion of the space-time, but they're still able to compute to the index of specific 2-dimensional CFTs. Now, there's a caveat to saying that the partition function in flat space is now equal to the index of the CFT, which is that there are actually more solutions that we've encountered previously that contribute to the index in flat space than to the index of the individual CFTs. So you could take the multi-center solutions that I talked about earlier, uplift those. You could get black holes and black rings living within the same space-time, and each one of these objects has an associated index to them. And the overall index of a theory is a sum of all possible combination of indices for the subsystems. So it would be very interesting to see how these multiple quantum systems interact in the same picture. So notice that they don't even need to be the same CFT, and they don't need to live in the same number of space-time dimensions. The quantum system that's associated to a black hole probably is not the 2-dimensional CFT, and even if I take two black rings that are separate, they could have different central charges. They could have different D4 brane charges, so there is no requirement that they be the same theory. So in some sense here we're computing an index in some kind of sum over theories. And a final outlook is that in a previous paper together with Toriachi and Morphy, we localized the gravitational path integral in supergravity in the 0 temperature limit to understand the degeneracy of extremal black holes. And you could ask whether you can do the same thing for the indices that we just computed. So instead of just focusing on the ADS2 region, you could perhaps try to compute the degeneracy directly for the flat space index. And in principle, if you do this in high enough dimensions, at the same time, you can compute the indices of all supersymmetric holographic CFTs that we know of with a single calculation, right? Because let's say if we're in 10 dimensions or 11 dimensions, these flat space indices, depending on our choice of charges, should really capture all the theories that we know about in string theory. Okay, so that's it. Thank you very much.
Can you say it again? How do you isolate the contribution from each CFT since you only know the sum?
So there's a little bit of guesswork, but essentially it's that the saddles that capture the contribution from the partition function of a single CFT in the zero temperature limit just have a single ADS throw. Yeah. So, and there's other ways you could go. So there's another phenomenon that's very interesting when you have multi-center solutions, which is the phenomenon of a phenomenon that's called wall crossing, in which you can tune the scalar fields at infinity in a way that some of these solutions just disappear. And sometimes you're left with the index of a single solution.
In a zero temperature?
No, even at finite temperature. Yes, people have studied that at zero temperature. We can study it at finite temperature now. And what the contribution of that single solution would be the contribution of a single CFT. Yeah.
These finite temperature strange the solutions, they don't have this gravity run.
Well, I'm not exactly sure how the instability is defined since we're in Euclidean signature. And usually these instabilities this kind of disappear when we look at BPS solutions, but I'm not entirely sure. We haven't checked. Yes, but it's still BPS. So, yeah.
Ask a related question. So suppose we didn't know what MSW. Suppose we didn't know our decoupling argument. We found these solutions. Would we have inferred that there's a 2D CFT?
I guess if you were smart enough to compute the index of the 2D CFT by yourself, or if you would have listed 2D CFTs, computed their indices, and saw that it matched with this answer, I assume so. Yes.
I mean, that just
Sorry.
that could just be coincidence. That could be an argument to say why there's an underlying transfer. Because you have great feature upstairs. In M-theory construction, the brain feature set, we can run an effective CFT description, decoupling all the massive mode.
Yes.
That will be the CFT that governs the low energy dynamics in the appropriate sector, and that to compute the degeneracy of index in that context. That's directly with the blackboard. That was MSW argument probably. But here, once you specify boundary conditions, as you said, you just specify for the boundary condition, and then come to the index. The gravitational path is the cell index.
Yes.
But in some sense, I'm wondering why there is whether there is a disconnect between that picture and the decoupling picture.
I think the connection just comes from the fact that as we tune beta towards infinity, that we know that the index is independent of beta, or has this trivial beta dependence when it comes to gradient mass. And as you tune beta to infinity, we do approach this decoupling limit. So in some sense, it's an argument that relies on supersymmetry that connects these two pictures, the picture at finite temperature and the picture at zero temperature. But yeah, nevertheless, it's good to at least know some observables for which flat space holography makes some sense.
Yeah, Rory, am I getting it right that at finite temperature, you're grading these CFTs, you will in a sense of grading indices, grading more?
For now, no. Yeah, that there's a specific observable in flat space that sees the underlying quantum system even away from the decoupling limit. Yeah.
You said about there being these curved solutions that are still specified. Is that extent the curved geometry of the solutions?
That's a fantastic question. I don't know. Perhaps. So there's a subtlety when going between flat space that might indicate what we should do when we go in PS, which is that the insertion of -1 to the F, or yeah, the thing that chemical, you have to turn on more chemical potentials than just the 2-pi rotation. It's the same. Well, the reason why is because the index is not -1 to the F e to the minus beta H. There's -1 to the F e to the minus beta anticommutator of Q and Q bar. And the anticommutator of Q and Q bar in the superconformal algebra contains more stuff than the dilatation operator. So to compute an index, typically in ADS, you need to turn on more things. And I think the question in de Sitter would be, what's actually the correct ensemble that we have to think about? Well, I don't even know how to think about ensembles in de Sitter to begin with, but if I did, I would ask what was the correct ensemble that I need to compute for there to be a solution. But I think maybe another approach is you could go the other way around and ask, what is a solution that has a killing spinner that in Euclidean signature is closed, is a closed manifold with no boundaries? And I don't know the answer to that question, but I think it's very interesting. Yeah.
So you just talked about like areas and non-shell actions and leading order in G. Is there any prospect of doing long loops? And I guess you'll have 0 nodes that come from integrating over this moduli space and
Yes. There is. First, when we discuss long loops, it's important to make a distinction between things, namely an index and what's called a helicity supertrace. The index of something in flat space technically oftentimes vanishes because there's 0 modes associated to translations, and those have fermionic partners that are also 0 modes. There's way to lift those, and that's what a helicity supertrace computes. Now, if you that also kind of gets rid of this translational mode. If you get rid of that, I think there's an argument that tells you that I haven't fully worked this out, but I think there's an argument that tells you that the one-loop determinant can be obtained from the fixed point theorem. So it only depends on the properties very close to the horizon. At the north and south, the fixed points of the killing vector that's associated with the killing spinner squared are the north and south poles of the black hole. And I think I don't have a very clean argument for why that's completely temperature independent, but at least it's optimistic that we can compute it using this fixed point theorem.
does it involve some volume of the moduli space and multi-center solutions?
Yeah, in the case of multi-center solutions, it would include this fixed point. You would, in addition to one-loop determinants, you actually have a non-trivial moduli space of solutions, meaning that you have a compact space of 0 modes. We're working to understand what the volume of that moduli space is, but it's hard because we don't know what the correct measure on that moduli space is. But maybe I should give, I think mathematicians give us one clue for what this index of multi-center black holes actually is. There's a formula that's derived by Kontsevich and Soibelman that predict the exact values by which indices jump. So it predicts and these jumps are associated to losing a specific set of solutions as you change the moduli. And I think that should give a clue, or that should give something to match what the volume of